So if I'm doing a science experiment in this room, and it gets hit by some noise that causes randomness. And then 5 years later, somebody somewhere else does the same science experiment somewhere else that gets hit by other noise. You will usually say that these two experiments are independent. So what events that happened in one experiment are not going to change your beliefs about what might be happening in the other, because the sources of noise in these two experiments are completely unrelated. They have nothing to do with each other. So if I flip a coin here today and I flip a coin in my office tomorrow, one shouldn't affect the other. So the events that I get from these should be independent. So that's usually how independence arises, by having distinct physical phenomena that do not interact. Sometimes you also get independence even though there is a physical interaction, but you just happen to have a numerical accident. I mean, A and B might be physically related very tightly, but a numerical accident happens and you get equality here. That's another case where we do get independence. Now, suppose that we have two events that are laid out like this. Are these two events independent or not? Okay, I mean, the picture kind of tells you that one is separate from the other, but separate has nothing to do with independent. In fact, these two events are as dependent as Siamese twins. Why is that? If I tell you that A occurred, then you're certain that B did not occur. So information about the occurrence of A definitely affects your beliefs about the possible occurrence or non-occurrence of B. When the picture is like that, knowing that A occurred will change drastically my beliefs about B, because now I suddenly become certain that B did not occur. So a picture like this is a case actually of extreme dependence. So don't confuse independence with disjointness. There are very different types of properties.
Question?
Yes?
So I understand that explanation, but the probability of A intersect B is 0, right? Because they're disjoint?
Yes.
But then product of probability A times probability B, one of them is going to be 1, as you said it happened, the other one is 0.
No, so suppose that the probabilities are 1/3, 1/4, and the rest is out there. You check the definition of independence. Probability of A intersection B is 0. Probability of A times probability of B is 1/12. The two are not equal. Therefore, we do not have independence.
Right. So what's wrong with the intuition of the probability of one being 1, of A being 1, and then the other one being 0? Because in the definition, is that stuff?
No. Probability of A given B is equal to 0. Probability of A is equal to 1/3. So again, these two are different. So we had some initial beliefs about A, but as soon as we are told that B occurred, our beliefs about A change. And so since our beliefs change, that means that B conveys information about A.
So can you not draw independent events on a Venn diagram?
Can't hear you?
Can you not draw independent events on a Venn diagram?
No, the Venn diagram is essentially never enough to decide on independence. So the typical picture in which you are going to have independence will be one event this way, another event this way, and you need to take the probability of this times the probability of that, and check that numerically is equal to the probability of this intersection. So the numbers, it's more than a Venn diagram. Numbers need to come out right.